Welcome to this webinar on modeling rotating electrical machine using COMSOL Multiphysics. My name is Nirmal Paudel. I'm one of the applications engineer working off the COMSOL office in Burlington, Massachusetts. During this webinar, we will go over COMSOL workflow on modeling a rotating electrical machine using AC/DC module. We want this to be interactive, so please feel free to type in your question in the chat window, and I'll try to answer them as they come in. So this is the product suite for COMSOL Multiphysics 5.2a, which is the latest version. So we have on the top is a COMSOL Multiphysics base package upon which everything else is built. And on the left hand side, you'll see all the physics-based modules categorized on electrical, mechanical, fluid, and chemical. And also there is a multi-purpose module in the green, and interfacing products on the right hand side. So today we'll focus on AC/DC module, more specifically for modeling electrical rotating machine within this module. So in AC/DC interface, there are altogether 11 physics interfaces, as you can see here under AC/DC folder, but there are two interfaces actually under heat transfer. That's for Joule heating and induction heating. So here, electric current in cell, and electrostatics. These physics are used mostly for modeling resistive and capacitive, and electrical circuit for modeling lump parameters to connect with the FE model for modeling the circuits. And then also for modeling magnetics, we have 4 different interfaces here, whereas the magnetic fields and magnetic field no current physics actually are combined together in rotating machinery interface to give a specialized interface for modeling this kind of machines. Now this interface actually, or the modules, support different types of studies: stationary, time-dependent study, frequency domain study, and also there are some studies for like coil geometry analysis and small signal. So if you want to learn more about what are the capabilities of this AC/DC module, please go to this blog link below here. So the common AC/DC applications, as you can see here, you can build or model resistors, capacitors, inductors, and coils. They're common in, for example, in transformer modeling or wireless charging and so forth. And also if you're modeling a permanent magnet or the fields around it, that can be done. And today we'll mostly focus on the motors and actuators, also specifically on rotating machines. And if you want to also design or model a heat transfer on those machines, obviously you can do that using electromagnetic heating. So as I just mentioned, the rotating machinery magnetic interface is a combination of 3 physics. The magnetic field physics, which is based on magnetic vector potential formulations, and then magnetic fields no current, as the name implies, based on the magnetic scalar potential formulation. Here there's no current carrying conductors or induced current in it. And also there is a moving mesh combined in it to have a prescribed position or velocity of the rotor in the model. So the rotating machinery interface only supports stationary and time-dependent studies. And here are some of the equations where Vm is the magnetic scalar potential within the scalar potential region, and then in the magnetic field, which is a vector potential region, we're solving for vector potential A in the stationary case, and this is the equation in time domain. Now this is the basic intro of this interface. So let's go further in the modeling of rotating machine, and these are the key steps that no matter what you are modeling, But more specifically for rotating machine, first of all, you have to decide what is the space dimension that you want to work with, 2D, 3D, and then in the geometry, you can build your own geometry within the COMSOL, or you can import it from other CAD softwares. But keep in mind that when you import, make sure that you have two objects, separate objects, one for the stator and the rotor, and finish the geometry using form assembly. Also, we do recommend that you always take a deeper look into the symmetry. That will significantly reduce the computational cost later on. Now, and the next step obviously is to assign the materials. You want to assign a magnetic materials, or you can also assign permanent magnets, for example, or assign the lamination and different conductivity in the coils and so forth. So that will be taken care under material assignment. In the physics setup, as I mentioned, it's a combination of vector and scalar potential formulation. So you have to decide on which region to solve what. So also in modeling the coils, you have different choices: stranded wires, coils, or solid conductors. And obviously you want to drive them with a current voltage or with the external circuit, or connect the load on the circuit as well. Then also rotational, you want to prescribe an angle or velocity. If you want to include the dynamics, you can always add the global OD to include the dynamics of the machine. Then you can obviously use the automatic meshing, but usually we recommend to do a little bit of customization if you're modeling a sector models. So I'll demonstrate that how to set up a customized mesh today. And in analysis, you want to have stationary time dependent. Also, if there is a coil, multi-turn coil, you also want to use a coil geometry analysis to get the coil configuration correct. Then solve and post-process. There are some already predefined variables for post-processing. For example, you can post-process torque, induced voltage. Obviously, you can also calculate the losses. For example, copper losses, hysteresis losses, also core losses. And if you're modeling a motor, you want to know the speed of the motor as well. So things like that. So let's move on to the demo. Today I'm going to quick demo on the permanent magnet AC generator, single phase generator in 2D first. So this is a geometry on the left hand side. It's a full cross section of a single phase AC generator. We have a stator here, iron, which we will assume as a laminated steel, iron for this, and also for the rotor. And we have a permanent magnet radially outward and inward. And then we have the windings through this stator slot with black and red representing opposite polarity of the currents. Now, instead of modeling this whole geometry, what we can do is cut sections of it and just model a sector as shown in this image on the right. So we include only one piece of the permanent magnet and a sector of the stator and the rotor. So, and there is for this, we will assign a periodic boundary conditions on either side of the sector cut and assign a sector symmetry on the interface between the stator and the rotor. So for this one, in the stator, we're assuming that there are 100 turns of wires with a cross-sectional diameter of 3 millimeter. These are the stranded wires, so we'll be neglecting the eddy currents on them. So it's a homogenized approach which can be done in COMSOL using a homogenized multi-turn coils. And for this 2D modeling, the length of the generator is 0.4 meter, and we will calculate the induced voltage in this on the coil. So since we're modeling only the sector, in the post-processing, you have to just multiply with the number of sector to get the total voltage output. The alternate method, again, you can also cut in a different location and just include half of the magnet on either side, radial in and out. But this is just a different way of modeling it. I'll just do a quick demo on the first method. So let me switch to the software here. So this is the screen that you'll see once you launch COMSOL Multiphysics. So first thing first, we'll just choose the space dimension. It's going to be 2D modeling space here. Click on 2D, and the physics that I'm going to use here is the rotating machinery magnetic. Click on Aid. And in the next step, choose the study. I'll choose the stationary for this one here. This is the COMSOL window. Now we have a model builder on the left. We have some ribbon with tabs, definition, geometry, material, physics, mesh, etc. on the ribbon. We have a graphics window here where mesh and results will be displayed. Now, what I'll do is I'll first load some of the parameters that I have defined for the model. And I can simply type them here, but to save some time, I'll load from the file. So these are the parameters here. The length of the generator, the RPM, this is the diameter of the stranded wire, number of turns, and the number of sectors. Then go to the geometry. Here, if I right click, I can actually import the geometry, or I can also build everything in COMSOL. But here I'm going to do an insert sequence. So these are the steps here. First of all, I just import a full cross section and then rotate it by 22.5 degree. Then I create a polygon around this one. Both are the same polygon actually. I'll do the intersections of this polygon with the first part, actually has a rotor, and the stator as a separate part. And also do the second intersection between the rotor and that polygon. So I end up getting this nice sector with two parts, the rotor and the stator part. Then finally finish with a form assembly, build all. So then it create an identity pair, which we can see it under definition here. So one thing to make sure is that the source and destination are correctly assigned. So here, here it's difficult to see which is boundary 9 and 18, but what you can do is go to the view and show geometry level and click on domains or boundaries. Then if you zoom in, you'll see that 9 actually is the boundary that's towards the rotor and 18 is towards the stator. So we always want the source boundary to be the stationary boundary. So, and then destination to be the moving boundary. So in this case, what we have to do is we have to show up the source and destination from 18 and 9. Then I will not need this one, so I'll just disable this. Now, once we take care of the identity pair, I'll just quickly do a selections for the boundaries that I'll later on use in the meshing and also in the physics setup. So right-click selections, and then do the explicit selections to the boundary. Let me just click the boundaries, periodic boundary condition on the rotor, and name this as a periodic boundary condition on rotor. Now let me just duplicate this one and clean this. Do the same thing for the stator side. Stator. I'll just keep doing this one, duplicate. This time I'll make a selection on these periodic boundary conditions on the short side. and duplicate this one to do the on the destination side. I'll just clean this up, and I've checked this group by continuous tangent. It will actually grab all these edges on the same line. Here actually there are two parts, that's why you have to click on two of the boundaries to group together. So we have the source and destination selected, and let's do one more selection for the sector symmetry. And finally, I'll create one more selection in the domain for moving domains or rotating domains. All right, all the selections is done. The next step I'll do is create a cylindrical system to define a magnetization in radially outward or inward for this permanent magnet. So to do that, I'll just right-click here, go to the coordinate system, and do a cylindrical system. So obviously the origin here is 0, 0, which matches with my current geometry. I don't have to change anything. So with that, let me minimize this here and move on to minimize this geometry and move on to the materials. So what we want to assign is, the first material is we want to assign an air material. If you right click, air material, go to the built-in, grab air, and click A to the component. By default, it will assign air material for all the domains, but also we want to assign a soft iron. There are two soft iron with losses and without losses. The without loss means the electrical conductivity is 0, and with loss means it has higher electrical conductivity. So I'll assume this as a lamination stator and rotor, and the conductivity is very small, or 0. Then assign on the rotor and stator. I'll minimize this. Then it will ask for the relative permeability here, so I'll just safely ignore this for a while because I want to use a BH curve on those nonlinear material. So let's move on to the physics and the physics settings. So we will first define the domain level features. That means add a permanent magnet first. If you right click on the top, you'll see all the domain level features. There is a scalar potential and a vector potential. Let's go for the vector potential and Ampere's law on permanent magnet. And now we want to choose a cylindrical system that we just add. So here, change it to cylindrical system. And to define a permanent magnet, there are two options. You can either have a remnant flux density or magnetization. So I've included a few slides discussing about this at the end of these slides. You can actually download and look for both the options. But here I'll go for the remnant flux density and choose the permeability to be 1.05, which is a fair number for rare earth permanent magnets, and have the remnant flux density of 1.4 Tesla. That is all I need for the permanent magnet. And I'll do the same thing, but for iron, get an Ampere's law. Actually, I can rename the first one here, not to confuse. And here, let's rename it to be iron. Then we select domain 1 and 5, go to the relative permeability under a constitutive relation, then change it to BH curve. So the BH curve actually is coming from the material here, soft iron. Now if you expand the material, you'll see the BH and HB curve, both included here. The reason why we have a HB curve is because we're formulating or we are solving a vector potential A as a solution variable. So from A, we get the value for B before we get the value for H. That's why we need a HB, which means H as a function of B. But if it's a magnetic scalar potential formulation where we solve for a magnetic scalar potential, and from there we get value of H first, then B. That's why we need a BH curve. So if you take a look at this curve data here, it is a tabulated data with B and H, and you can of course load your own measurement data, or you can, if you need, you can also save this data somewhere else. And it also includes the effective SB and BH curves for modeling the same BH curves in the frequency domain. So we have done a webinar in the past about the nonlinear magnetic materials modeling, and if you would like to learn more about it, please go to our website and look for that webinar. And also in these slides, I have included a few slides with the resources available for that type of nonlinear materials in COMSOL. So that is for the iron. Now, the next step is to have a coil model. Right-click here, let's go to the vector potential and assign a coil on domain 6 and 7. I will just leave this as a homogenized multi-turn coil, check and group. So here, what we are assuming is the current through this circle on domain 6 and 7 is homogenized, and we've checked here group options. That means these two windings are connected in series. So there is a current going in from this and coming out from this one. So to take care of that, we have to reverse the current in one of the coil. And also here, we want to calculate the voltage, but you can also connect to the circuit if you want. So I'll do the circuit voltage here, and I'll use the variable that I've already defined, non-term, which is 100. And now this is the cross-sectional area of the stranded wire. You can choose a stranded wire gauge or American wire gauge, or have your diameter defined here. This is the variable or the parameter that I've already defined, 3 millimeter. Then we're done for the coil part, and in the next step we will define a prescribed rotation or rotational velocity. There are two options. Prescribed rotation means if you know the fixed rotation ahead of time, you can do it. But if you have a angular motion that is linearly growing with time, then you need to assign a rotational velocity here. On rotating domains, this will be RPM. These are pretty much for all the domain level features. And in the boundary level features, let's quickly add on the pair, scepter symmetry on this identity pair, and number of sectors, and continuity or anti-periodicity. So if you recall the previous slide, we saw that the magnetization directions on this sector and the adjacent sector actually is in and out. So it's an anti-periodicity condition. Then let's add a periodic boundary condition on rotor with anti-periodicity, and also periodic condition on the stator with the anti-periodicity. So this is pretty much what we need to do for the rotating machine. Now we can then connect with the external circuit. To do that, I would like to connect a load circuit to it. So add physics, and under AC/DC there's an electrical circuit, add to the component. Then here as if you go up here, you'll see that it's connected to the external U versus I. Then what we need to do is connect a external coupling U versus I, and then link it to the coil, but make sure that one of the side is actually connected to the ground. And we connect external load resistor in series with this one. Can have any number, but I'll pick it to be 10 ohm for this one. So that's the connection of the load resistor to the generator. Now let's move on to the meshing. So for the mesh part, I'll quickly set up a mesh here to be finer and to the user control mesh, and duplicate this one, have a boundary, and choose boundary 9, which is our destination, to have a custom size of 4 mm, and duplicate this one and have boundary 18, which is our source side, to be a little larger. So usually the solution will be more accurate if you have a finer mesh on the destination side compared to the source side. Also, for the periodic meshing, we would like to have a same mesh on the source and destination side. Let's create a edge mesh on the boundary on the source side, and duplicate or copy that on the destination side, from the source to the destination. So we copy the same mesh on either side of the periodic boundary condition, then free triangular, build all. So this is the mesh we'll work with. And so finally, in this stage, in this study state, we already have a stationary study. This is needed because we have a permanent magnet in the model. So we want to make sure that before we solve a time-dependent study, we want to make sure that there is a field from permanent magnet already existing before time t equals 0. So now we will add a time-dependent study, time-dependent, and change the range from 0.25. Let's assume there are 51 data points that we want to solve for. And this will automatically get the solution data from stationary one to the time-dependent one. Like the initial value, the final solution of a stationary study are then used as the initial value for the time-dependent study. So then we're ready to compute. So it's going to take a minute or so. So to save some time, I'll just load a solve model. So it's the same model, everything else here. A little bit on the results. So the data set, actually the solution are outputted on the material frame, but you just need to change it to a spatial frame. Then also create a sector with a number of sectors, and then make sure that you click on this invert phase while rotating, because it's anti-periodicity conditions that we used to correctly have the phase information here. Then we create a magnetic flux density on the stator for the sector model, and a contour plot for vector potential. And then now we use the same plot group, but for the full model, the source data is a sector 2D, and the voltage output, voltage induced. We have two voltages here. The first one is the induced voltage in the coil. The second one is the voltage drop on the resistor load. So they pretty much whatever is induced in the coil is dropped on the load resistor. And the current in the coil, which is the maximum current, is about 8 amps. Now, to calculate the losses, so losses, we have some equations here. Now, the equation here, the first one is the power loss in the green one is the power loss in the load, but there is also a small power loss in the coil, which is minimal, because we don't want to design a generator winding that is lossy. But if you want to do a average loss here, there is a time average operator which you can use. It can be used to do to find a time average of in the entire time period. So this is for the 2D model. So let me take a look at some of the equations here. So there's a question from Richard. Is it possible to model BH curve temperature dependencies? Yes, COMSOL can actually handle the BH curve that are a function of temperature dependent. Now, in this case, I'm not considering any temperature dependency in the BH curve. But, if you would like, then that will be a two-dimensional data with a dependency on the temperature and BH relation. So that can be done, yes. So there is another question from Jerry. Do you have any example of induction generator? We do not have any examples on the induction generator, but I'll briefly mention about the induction motor, which essentially, you can pretty much get the idea of that and solve for the induction generator as well. Let me just quickly jump into a 3D model. In the 3D generator model, we have the same generator, but now in the full 3D. Instead of modeling the entire 3D geometry, we just cut sections of this. So that means we are solving only the 1/16th of the model. So this is the sector that I will be solving, or I'll open the model that with this information here. We have the stator iron, rotor iron, magnet, and the coil. So a few extra things that you have to be aware of is about the vector potential and scalar potential formulation in 3D. Now, the way it is set up is the red is a vector potential region and the blue is the scalar potential region. So here in the red region, we also have a multi-turn coil domain. So we always want to make sure that the coil part is embedded on the vector potential region. And since the scalar potential region do not support any current carrying conductors, so it means it should be a divergence free. Now we also have to make sure the other requirement is that the identity pair, which is represented here with the white line, so the domains or the region on either side of the identity pair should be a scalar potential. So with that two important aspect of the modeling in 3D, then we can move on to the actual model. So let me just quickly bring in the 3D generator model. So this is a 3D model with the same parameters. So I'll just go directly into the physics here. Now, what we have done here is there is a mixed formulation boundary automatically connecting the vector potential and the scalar potential region. So anything on the left is a scalar potential, on the right it's a vector potential. So we have a multi-turn coil, numeric type with input and output. That's how the current is flowing. And then we have a magnetic flux conservation on the rotor air, flux conservation on the magnet, and we have a nonlinear pH on the rotor, and also nonlinear on the stator. So now in this case we're using SB curve, but for the rotor we're using the BH curve. Now also there is a prescribed velocity, and in terms of the convergence, we also have added a gauge fixing for A field. This is usually required if you want to do 3D simulations on the electric machines. And we also have two periodic conditions on the stator and the rotor side, and sector symmetry. So one additional the constraint that you have to impose on the magnetic scalar potential region is you have to have a point constraint somewhere in the model to get a unique numerical solution for the scalar potential region. And in terms of the materials, you always want to make sure that you have some small finite electrical conductivity in the air and also in the iron. So these are the things that you have to be aware of in terms of the convergence. Now also in the meshing, it's heavily customized. It's the same idea, you have the source, destination a little bit finer, and then also you can do a lot of sweep meshing on the region. Like for this example, we have a sweep meshing on the air region outside of the identity pair. And also you can do the sweep meshing on the coil itself. If you hide here, you'll see the sweep meshing on the coil. And the same steps here. One extra step is the coil geometry analysis. This is needed because we have a multi-turn coil with numeric types. And the results. We also need to do the mirror here because we're solving 1/16, and we just have to copy the results on the other side and do a sector of 8. So finally, we got some results in the 3D. And induced voltage in the generator. So there is a question, can we model material anisotropy due to lamination in 3D? Yes, that's a very good question. So the material anisotropy can be signed directly in the Ampere's law. For example, if you go to the Ampere's law, here in the permeability, you can change it to the user-defined, isotropic or anisotropic. It could be diagonal and so forth. You could do the same thing for electrical conductivity as well. So let's just quickly go to the resources here. We have written a couple of blogs on rotating machinery, which you can find in those two links, which is very comprehensive, and I definitely encourage you to go through those two blogs. Now from generator, let's move on to the motor. This is the induction motor example in 2D. It's one of the TIM benchmark model where we have a stator with a 3-phase current and laminated steel, and we have the rotor, which is a aluminum and steel, both are conductive. In this particular example, we have also included a dynamics, that's the angular speed of the rotor, and also the electromagnetic torque, load torque. As you can see here, this is the electromagnetic torque as a function of time, and we introduce an additional load torque after 0.5 seconds, and we notice the gradual increase in the speed, and after we impose an external load torque, then the speed slightly decreases. So this is something you can do in COMSOL. And also some examples on magnetic gears. So if you're working with magnetic gears, I would strongly encourage you to go to this blog link where we have actually done 3 different examples: coaxial magnetic gear, axial field magnetic gears in 3D, and also linear magnetic gear. And finally, if you want to create an app, means if you want to have a customized for your model, or motor or generator or any device, then the application builder tool allow you to have a customized user interface, and you can share the app to your colleague or to your customers using the application builder. So that's pretty much what I have. Let's take a look at some of the questions here. So there is a question from Antonio. Can we model a vibration of the motor? Yes. So if you want to do a vibration study on the motor, there are a couple of things you have to do. So COMSOL actually has, the acoustics and structural mechanics. These are the 2 modules that you would need. First of all, there is electromagnetic force that induces stresses, structural stress, and you can actually use that information to feed into the acoustic simulate the vibration. So there is a question: can COMSOL model linear induction motor or similar linear machines? Yes, COMSOL can do a linear machine design. Though the rotating machinery is not a interface that you'll be using, you can use a magnetic field physics and couple with the moving mesh. In fact, we have a couple of examples in our applications gallery. If you go to our website, to the applications gallery, then if you look for tubular generator or linear magnetic gear, then you'll find those 2 examples useful. So there is another question: can we model a superconductor motor or generator in COMSOL? The superconductor, for modeling superconductors, we have the magnetic field formulation interface, and we have one example of superconductors. It's a simple example, but again, something can be done, but we do not have any example at this point. But yes, certainly something that COMSOL can handle. So there is another question that I always have convergence issue in my model. How do I solve it? So the convergence in the model could be from many different issues. The couple of things that you have to be aware of in modeling a rotating machinery is, if you have coupled with the external circuit model with the FEA model, then you always have to make sure that you have a fully coupled direct solver. Same thing if you have a sector model, then you always need a fully coupled direct solver. And also, as I mentioned earlier, you have to now add a gauge fixing and also have a same meshing on either side of the periodic boundary conditions, and also the electrical conductivity that you have to put a small electrical conductivity in the model. And also, if there are eddy currents induced, you have to resolve them appropriately. So there is also another question from Vivek. Are there any examples on 3D rotating machine modeling? Yes, we do have a couple of examples that actually show the COMSOL capability in modeling 3D machines. And if you would like to know more, please contact us in the support. So there are a few additional questions that are unanswered during this webinar, but we'll try to answer them by our support. So thank you everyone for attending the webinar, and I hope you enjoy it, and I hope the slides will be useful in pointing the additional resources that we have. And please feel free to contact us if you need any technical support or any information from us. Thank you.